and start with, sorry.
I forgot to press record.
That's
But
okay.
good thing this was the most important.
Yeah.
I got it in time.
Yeah. Someone has questions in the audience?
Or feel free to ask them through the chat if you do not feel like asking anything directly.
So for me, I would like to start with Paul. Interesting review of the trend of new chemicals, new compounds developed in drug design, and how, based on what I had read, how the increase of molecular weight and how to maintain to control the lipophilicity. So is it counterintuitive or is it really the reality?
Well, I just showed a bunch of facts, Laurence, didn't I? That was what was seen. I don't know about counterintuitive. I'm not quite sure what you mean by that. Can you?
No, it's just because so when people they think beyond rule of 5, you know, the first thing in the industry is you will look for high molecular weight. You will look for a number of H donor and H acceptor.
Yeah.
And so when you say, oh, so that means, you know, instinctively people will say, oh, that probably means we will have a higher log P, which doesn't seem to be the case based on all the review. And I was wondering, is it counterintuitive or is it also because I know you base the lipophilicity based on calculation models, but also I was wondering if somewhere there was also a kind of a change in the way you measure lipophilicity, and if you have a more accurate way of measuring lipophilicity, you don't see a change when in fact, you know, maybe there is, I don't know.
Yeah, there was a big caveat to everything I said, and it was calculated, absolutely. And that was a huge caveat. And as you showed, there are lots of elegant ways to measure, which are essential to use in projects. And you know, it's very probable, and I think we all know, that as you get into more extreme space, you know, the measurements will start to be more problematic. So the calculations will start to be more problematic, and you'll begin to need to measure. But you know, if you think about it, molecules are getting bigger, but to keep the polar non-polar balance in the same place, you have to increase the polarity as well. You know, and I think, and listening to what you said, Laurence, I was just interested because the way we're looking at that and what the data shows you is that's mainly achieved with H-bond acceptors. That's what it showed. And H-bond donors sit there kind of neutral, not doing very much. And does it mean that those H-bond donors are just unimportant? You know, they just don't matter very much. And you do most of your work in optimizing molecules to get into the right place by adjusting the polarity through, you know, the H-bond acceptors and H-bond basicity as being important parameters or not. So, you know, I must say, reading Peter Kenny's recent review made me think more about that. And hearing you, I think you showed in some of your analyses some quite interesting effects of donors and acceptors under certain circumstances there, which might not have lined up with what I said, actually, very much. And I did notice that. So thanks for that. It was really good to see, actually. So I think that was a little point for debate for me. What's how do we get to grips with that, and how do we understand that better? And are in fact donors, as Peter was suggesting, actually more permissive, and you could use them more? And I don't know, you know, all of us H-bond donors get a bad rap in medicinal chemistry. They're always told to get them down, and it's certainly getting in the CNS, it looks that way. But in other ways, you know, are there some questions to ask there? And of course, I think as Peter pointed out, you can't change one without changing the other. If you add H-bond acceptors, you normally can add H-bond donors, and the other way around, because an H-bond donor is mostly attached to an acceptor, although not always. So I think there's some interesting points there, and that you know, that needs a little bit more investigation, I think. I didn't answer your question really, Lauren, but that was on my mind.
No, it's good. Rob, you are on mute. We cannot hear you.
So sorry, I hadn't realised that bit was there. Yeah, I'll just add a little bit in that. So following on some of the things that Paul was showing, and thinking about nature, because after all, we're asking these compounds to interact with living things, and we're just animals ourselves, and and everything that has come through evolution. And one of the points that we made in one of our papers, when I did with Chris Timworth in 2020, is if you look at a random set of compounds, there's fairly much a reasonable correlation between lipophilicity and molecular weight, which is maybe why some of these dogmas have come along. But if you actually look, as Paul elegantly showed again there, and we actually showed in the paper using measured methods, and thanks to Clara developing the chrome log D things at GSK, we were able to look at some of the bigger molecules, and there are plenty of them in GSK, that are higher molecular weight. I hesitate not to use beyond the rule of 5. They're higher molecular weight compounds, and actually the ones that were permeable and all the rest of it that we're seeing in the evolution, and it fits with the AbbVie rule of 5 and things. I don't know if Phil and Rishi are both on the call, but that I like, and it's just showing you that nature recognises these things, and we necessarily have to control lipophilicity out there.
Yes,
I'll put that in tomorrow.
It is an interesting thought, Rob. We know, it's other people have a different point of view. Remember the Merck paper that came out a year or two ago, which basically said we don't want to restrict chemists by lipophilicity. We don't want to do that because you can actually find drugs in all kinds of lipophilicity space, and you can solve a problem if you're diligent enough. Whether lipophilicity is high or low, you can still solve the problem and find a candidate, which is what they said. Now, that was an interesting and different point of view, wasn't it?
Well, it comes down to our conversations, Paul, and the point you made there about the regression to the mean. I think we've forgotten to look in other places, because everything that's been done has been done in a very homogeneous way for the last 20 years, maybe 30 now, into the 1990s, 25 probably since HCS really came in. But that's perhaps a symptom of what's been there, that people aren't open-minded enough to look in other ways, and we cannot be too prescriptive. We can observe trends, but as the point we made in the last paper, antibiotics are in a very different space. And I think people need to be brave, and I think that if there have to be rules, guidelines, principles, whatever you call them, they're going to change by target. I think your data show that, and we've now got the ability to measure these things with more confidence with these new methods. There's many ways of understanding it, and I think that will be the beauty of the places that chromatography can take us.
Yeah, may I say something? I was the person who asked Paul. Nice to see you again, Paul.
Hello, Clara. Good to see you.
Yeah, I am here close to GSK still, but that I asked the questions. I liked very much your overview. I didn't always know the compounds which were studied, how many were on the slides, but I liked very much that a lot of properties remained constant, and I think we should somehow summarize it, which is what is increasing. For example, the H-bond acceptor groups are increasing, which are decreasing, the size is increasing, which is a very interesting, but Paul highlighted that the ligand deficiency still didn't change too much regardless of the size. And it is a very interesting question, that how these properties relate to each other. When you increase the size, obviously lipophilicity decreases more by default. The size makes you have to create a bigger cavity in water, which makes much more energy than creating this cavity in a non-polar solvent. So obviously there is a relationship, but with the size, there are some hidden polar surface area we can, change. So when we do calculations, I do a lot of measurements for larger molecules, peptides, bicycle therapeutics. We published papers together, and the calculated lipophilicity was -10. And actually what I measured by chrome log D, it was around 1. So because a lot of polar groups were inside and covered. But it would be nice as a summary of your talk, if we can put on the LinkedIn, what are the properties, what you observed didn't change in the past 10 years, and which has some certain new trends. Because I think you are right, you answered the questions which didn't change. It must be an optimum. That's why everybody goes there.
Yeah.
And may I say something to Laura's talk? I really enjoyed it. It was so nice summary of all my 20 years of even longer work, what we did at GSK. But is slightly different, but you summarized all the aspects of chromatography. And as you know, I love chromatography, and I believe that a chromatographic distribution coefficient is very similar, more similar to the biological distribution, because these are on a large surface, they are dynamic equilibrium, shape is also affecting what we are measuring, not like the octanol water partition. And now with the large molecules, what is happening, these molecules are on the interface of octanol and water. So we don't really know when we measure an octanol water, is it a real partition? What is going? Maybe 90% of our molecules are in between the interface, partly in the lipophilic, partly in the hydrophilic phase. I just don't understand still why you don't go for a gradient, because it seemed to be, a very pragmatic approach. I was an academic as a background, 20 years, and I was pushed to this gradient, and I had the resistance like you and Julia Caron, and I talked to people. But I realized that it has a lot of advantage, because every molecule you measure under the same conditions, the same gradient, you don't extrapolate you never get exactly like octanol water. So I wouldn't bother really to imitate our system to the octanol water, rather to read the C18 partition or albumin binding, or the phospholipid or the IM partitioning. And we proved that the gradient retention is equivalent or very close to the isocratic. Moreover, there is this dry lab software, you probably heard about it. From 2 gradients, they are precisely, you can calculate the isocratic measure. And you mentioned that you for the E log D, you improved a lot with this alpha log D, but you also do a gradient to be able to identify which 3. So if you do the work, why you just don't use that? It would be cheaper. But
you are absolutely, you are right. It's just because you need to start. So it's also historic, and you work with clients, so they are, you need to show at one point that the alpha log D is with E log D. And yes, I would say we will probably go toward the gradient at the end of the day. We just need to do more studies to make people confident that they are the same. But yeah, you're right. It has been shown that gradient and isocratic are the same. It's just when you want to study at the molecular level, I would say, gradient is always changing conditions versus isocratic, it's always the same. But what is the closest to the in vivo? If we want, and you're right, if we want to mimic, to relate to permeability, how a compound is going through a membrane, it's always evolving due to the gradient of the electric constant. So yeah, you're right.
I think what we need is a rank order, and if you use the same condition for then the rank order will be more precise than if you changing condition and extrapolating. This is just my view, but I would love to have, and if I have a chance this year to have an MSc student to do the gradient. Actually, one of my PhD students in University of Athens, he did some correlation between the isocratic and the gradient method, but I have got the dry lab software here, so we can do what it measures and how because you are right, I think is a big problem to convince our clients that the gradient is as good as the isocratic, because it would save so much time and I think is reliable and is good enough for ranking. Moreover, I believe that it is a bit more precise for ranking because exactly under the same conditions.
Sorry.
You probably remember that as a gradient, everything is changing, you know, it's very, very difficult. It's differential equations you need to get into the isocratic and so on. But we studied the pH change, the pK change, you know, we spent lots of time and all is one paper and one PhD practically, how the gradient changes the conditions and the molecules behavior.
Great. Good insight. Thank you.
Yeah, I don't know if I can add something because actually I enjoyed both talks, I have to say. Lawrence, it was very interesting, the part related to E log D. I was just wondering whether you had explored maybe other and different selectivities in liquid chromatography, because we have increasing numbers of stationary phases being released on the market. Actually, one of the, of the most interesting probably is Silic, because it's essentially used a lot, for instance, for maybe smaller peptides. And I was just wondering whether you could maybe sort of translate the concept for that class specifically using maybe different selectivities as well.
Absolutely. Yeah, absolutely. I totally agree with you. And there are more and more papers where people are doing, the different support from cyano, C8, Helic, absolutely. But again, so it's, you always try to get some, to work with references, right? So so what would be the best reference, and again, if you expand the chemical space, how can you have lipophilicity, or how can you correlate what you will find in chromatography with any properties, whether it's permeability or something else. And that's, I think that the fundamental problems right now is when you expand the chemical space, some of the techniques are limited. Permeability is what it is. We had this discussion last year with peptides and protacs. Is a permeability of 0.5 a very low permeability for protacs versus, because we always refer with small molecules. So it's the same. What would be the lipophilicity of a large molecule? And if we use another techniques, how can we make sure that what we measure is exactly, what's happening in vitro, in vivo, because we don't have any reference. And
of course.
And that's the danger of pushing the limits, but at the same time, that's the beauty of pushing the limits, because we have to find something different. But again, I think it's more, for me, the different, exactly as you say, different type of chromatographies could help really understand the behavior of a molecule in solution with the membrane in front of a tissue. That's what you are doing with the IM. That's what Clara is doing with all the biomimetics. That's what everybody is kind of doing with different supports and different interactions. Yes, you're right. Yeah.
And even maybe using different techniques as well. For instance, supercritical fluid chromatography. Well, obviously the work done by Jill Goetz and yourself. But also maybe exploiting the selectivity by using other experimental approaches as a whole as well might be interesting.
Yeah, absolutely. Yeah, absolutely. Yeah, more to do.
This is important with chromatography, that we have to have another method to compare with, and we can standardize, or we can find a correlation and how to get that number out.
Absolutely.
Is important. And standardizing, to measure everywhere exactly the same, because it's so versatile. We can change this, we can change the stationary phase, but how can we produce numbers which are we can exchange from one laboratory to the other? Absolutely. Is very important. And Giacomo said that the selectivity, which is very interesting, and Paul highlighted that these properties are not independent or relates to a bit of size, a bit of lipophilicity. And I liked, Lawrence, your block relevance approach, but we used that GSK was the Abraham solvation, which are very similar. Practically is the size, the H bond acidity, H bond basicity, and it reveals a lot of similarities. How you know, the octanol water and the low and the non-specific binding or drug efficiency, how they are very similar if you look at the contributions of molecular descriptors for these properties. But this is very good. It would be nice to standardize this approach or using similar, but I know this too is the most commonly used for sensitivity, and they are practically very similar.
Absolutely.
Because the block relevance is based on calculated Wordsworth, no?
Yes.
Yeah, absolutely.
And Abraham, they have I don't know who is doing this H bond acidity basicity. It used to be ACD. Or do you know who calculates the Abraham alpha, beta, and polarity?
I'm not sure, Clara. I'm not sure. He himself came up with a lot of measures for various groups initially, but I don't know where that is today. No.
Where do you get your H bond donor index? Just count the groups?
I don't think so. I think it is H bond acidity and basicity that's used.
Yeah,
the original log P. Sorry, go on.
In your slides, the H bond is just a count of H bond donor groups.
Those were it's not. Yes, it is a count. Yes, it is. It came from Swiss ADME.
The Swiss ADME.
Okay.
So it's a Swiss ADME, which I think is reasonably good. You know, so it's not the same as the Lipinski count.
It's not the same.
Sorry to interrupt. So we have an audience question. So I have one. How accurate are predicted LLE values? That is, if these values can be predicted for a particular series.
Well, LLE is composed of two things, the potency and the lipophilicity. So predicting both things, I think, might be a bit tough. Normally you have an experimental potency metric, and then you choose your lipophilicity metric you want to use, which can be all of the ones that have been discussed today. Actually, you can use whatever you like and whatever works. So it might boil down to prediction of the lipophilicity metric you use. But as we said, in a project, you should be doing some experimental measures. Once you've got that sorted out, you can then begin to predict in a project based on your own data. So that will be the way to go. I don't think that's a predictable parameter, actually, for those reasons.
No, so there are a couple of examples in our paper, Paul, where we compared, the outcome of the prediction to a measurement, and when you've got a measurement, it does tease things apart because predictions aren't always perfect.
It does, absolutely, Rob. Couldn't agree more.
There's no substitute for measurements.
There is.
People say their predictions are pretty good now, but some of them are.
Yeah.
But real data.
but once you, I mean, the way to go is once you've got a few measurements, you can establish your local model of your series, and then you may be able to use a predictor based on that, or even one of the predictors will be quite good. So I think the prediction. I guess those organizations that are lucky enough to have vast amounts of data, like GSK and AZ, now have predictive tools that are really quite good. That's the other side of it. Of course, most of us don't have those.
Good. We have so someone would like to ask a question. Junhu?
Yes, I really enjoyed this two talks today. It's very comprehensive. So since you talk about a PROTAC, this has become a new, more and more compounds come out as oral bioavailable. The targeting covers a lot of targets. So can you guys comment the permeability for this ghost membrane? They also compare the traditional small molecules. The mechanism is a little different, or what you show one example is maybe they go to the membrane, they form the your stego structure from an internal hydrogen bond or something transporter goes pretty. Basically, the compounds is 800 to 1200. That's very big if you compare with small molecules, but it's still oral bioavailable. It shows excellent efficacy. So can you guys comment? Is there any mechanism different, like transport from the memory?
I would say instinctively, so large molecules, you may not have transporters, but again, this is what you have some products. They are big, but they have, as Paul would say, a controlled lipophilicity. So they are really kind of low lipophilicity either way, because again, they are completely folded. It depends on their flexibility. The carbon sp3, you have the bridge in between, the PEG linkers or not. So how does it? So how is it? It's more kind of conformation a little bit for me, and how so they become like a skein of yarn, I would say, somewhere, and they can go through the membranes and permeability. There is one point. The other one is, again, we use exactly the same assays of permeability, so PEMPA, CACO2 for these large molecules. Is this the right assay? Because usually you have small permeability, or small compared to what we will gain for small molecules, but that must be enough for the compounds to go through and as you said, to be potent and to show some efficiency. So there is still a lot of, for me, there are still a lot of unknowns. I don't know what my colleagues think about it.
Well, answer one question to follow up. Just a traditional, like what you test, what's the permeability we use? Those should be pretty accurate, predict this permeability, or the just as a reference. This is big molecules. We don't know how the goes through the membrane.
No, we don't know how they go through the membranes, because again, the permeability data, you never see. I don't know. I've not seen. Maybe I'm wrong, but I've not seen products with permeability of above 20. So usually it's in the range of 0.5, 1, 3, which is not a lot, but might be enough, to have enough compounds to go through. Or is it because, again, we are limited in the way we measure permeability right now, and we absolutely don't know what's going on in vivo, and that would be more my opinion there.
I very much think that's the point, and I know when I got to the slide on beyond rule of 5, I lost my slide and I forgot to mention the AbbVie metrics, and of course I don't know if Phil is online. I think he might be, but they got very frustrated about the in vitro assays not being predictive for these very poorly insoluble compounds, and so they just went in vivo. Of course, it turns out many, a quarter of those, there's 1,000 compounds in that paper. It's a very important paper, that the AbbVie one. Over 1,000 compounds in, and bioavailability upper quartile value is 27%. It's a bit worse than the small molecule piece, or inside rule of 5 piece, but not much, And I think some AZ data is showing that for Protex as well. So there is something about, those in vitro assays for certain kinds of compounds not being so good. It could just be the poor behavior of the compounds more than the assay. But I think it's probably right to question the assays, as you just did, Lawrence, as well. Are they the right assays? And I don't know. Are people still using Pampa? It's not such. Pampa will not be the assay to use, I think, for these experiments. But it's a good one. It's a good question. What is the right permeability assay?
Well, I think most people you do the assay, you get the data, but you use in vivo screening. You just do the sample to see how the compound behaves.
Yeah. No, I certainly see that in projects that I work with. That some clients, when they're in this tricky space, It's just bypassing permeability completely and going straight to screening for pharmacokinetics in vivo, just like AbbVie did.
Yeah. And I don't think it's that unusual also to see maybe in literature data on CECO2 to be different for the same compound as well. So it happened to me several times to see even big discrepancies for the same compound. So probably also the interlaboratory reproducibility can be problematic, I will think.
Yeah, and even we don't even know how these compounds behave in solution in terms of solubility. You know, as you said, what are the parameters that will create some variations in the solubility, and do they aggregate? Do they create micelles because of this somewhere? You know, polar head, lipophilic tails. So that we don't know, and I think that this type of for me, this type of essay to introduce more and more for large molecules, because again, we absolutely don't know how they behave in solution.
Well, there are some data now that suggests you may get these small aggregates with bile salts that are starting to break the membrane down. You get this temporary breaking of the barrier, and that can help things get across. I think I think we're too simplistic when we think about permeability, either both to get inside the cell and to get and for absorption. And you know, of course, the elephant in the room is you know, are the transporters or the elephants. There's more than one transporter that's involved here. There's more than one mechanism, and I think we're starting to understand more and more about that.
Absolutely.
I have a question from Giacomo and Lawrence. What is according to your experience, what is the largest molecule what you confidently can measure properties by chromatography?
You mean in terms of log P or in terms of molecular weight?
Molecular weight. Because I sometimes I am asked to 20,000 and 10,000 molecular weights, you know, but what I found, I can get nice peaks. On C18 is quite okay. You can measure very large molecules, but IAM and albumin binding, it starts to get very broad peaks, and I think you have to have a gradient in that, otherwise it will just stuck on the column. What is your experience? I tell you mine, but I am curious about yours.
So for me, working on the regular columns porosity, you know, so between 1500 and 2000 was with this the porosity of 100 or 60 angstrom or 120. As soon as you go above this 2000, you have to change the porosity and to go through the 300 angstrom because it's so big that it goes through, and whatever you get is whatever.
Yes. Their filtration effect. Yeah. And Giacomo, what was yours with IAM?
Actually, yeah, I have same experience as Lawrence essentially, and I also agree that you need to introduce gradient dilution programs, because otherwise you have extremely peaks with extremely both fronting and tailing as well. That makes also the establishment of the retention time particularly, you know, problematic, because essentially if you have a broader peak, you cannot, you know, sort of spot and identify clearly, even if the machine does it for you, essentially, even the retention time start to be not as reproducible as you would have for smaller molecules.
I am very happy because I had 2000, up to 2000 molecular weight. I am happy to provide data above. It depends on the compound, whether it's
exactly
a narrow peak, because as you said, wide peak, we don't know the retention. So, but what will happen if the molecules will grow even further?
Yeah, it's a good question.
2000 is not good for a traditional octanol water, no, or a equilibrium dialysis protein binding. They are struggling to do measurements. So I was very happy that chromatography could cope with. But if they grow more, I don't know what to do.
But so then in that case, if it's to measure lipophilicity, we could ask the question, what does it mean to have a lipophilicity of 7 or a lipophilicity of 10? you know,
But they don't, because they are proteins.
Yeah.
You know, they
Yeah.
are not, they don't get lipophilic, but large.
yeah, okay, okay, you don't get, okay, so not lipophilic, but
Not
large, okay.
lipophilic, just large, and the peak shape is getting distorted. That's the problem.
Yeah.
Yeah, but I think with proteins as well, the main issue that you can see, for instance, in circular dichroism as well, is that when they become more complex, also the conformation that they adopt is so changeable as well.
Yeah,
And
yeah.
I think, of course, it has an approach in the interaction with the mobile phase, stationary phase. So I think it's a problem for the reproducibility itself of the measurements, because they really, even according to the external temperature, they can arrange differently, even in the column itself. There becomes to be included so many variables actually in the process that it's really hard to account for all of them, I think.
But that's what's happening in vivo, probably.
Yeah.
Paul, what do you think? Can we go for a bigger molecule than 2000?
Well, I just heard Clara's rule, less than 2000. That's enough space to work in, Clara. Well, I was struck by, these high molecular weight molecules, which are conformationally flexible. When they're in a non-polar medium, they can be folded up. And maybe and I think the important parameter, like people like Jan, I think who was online, Jan Chilbury was online, he's now talking about, well, what is the cross-sectional radius of that compound? Isn't that could well be a better metric than the molecular weight, actually. So, what's the dimension that's important as the molecule finds its way into a membrane? Is it the whole molecule or the narrowest part of the molecule? Now, I think those would be interesting thoughts in that high molecular weight space. But how you get to grips with all of that, you have to just begin to look at experimentally the conformations, as I think Jan and a few people are doing, in solution of these molecules, and do the NMR studies, look at the conformation ensembles, and get a grip on what they might look like. Sorry, Rob.
I was going to say, what are the biggest molecules that nature pulls into a cell? You're getting to the point of find a receptor, and phagocytosis takes over. Viruses have found a way of doing it, so something we don't yet understand.
It could be the mechanism changes altogether for some of these molecules. Well, proteins, for example, which can enter cells, it must be that mechanism. And it could be some of these extreme molecules are using it. It could be. But then why don't small molecules use it? There we are.
They might.
They might. What do we know? Not much. Anyone listening is getting depressed now.
Before we move on, because we conclude, because it's already kind of late, somebody else has a question in the audience? There is one question for Giacomo, but maybe Giacomo, it would be better for you to answer tomorrow. Somebody is asking about the log KIM. Is it something you would mention tomorrow? Can we
Yes,
ask?
for sure.
Okay.
Yes, for sure.
So can we ask this person to come back tomorrow? So that's the best way to get an audience for tomorrow. Yes, we have one person. Good. So I
and if not, well, I'll make sure to ask it so that
okay,
that it can be accessed through the recording.
Okay, good. Unless you have who wants to have the conclusion for the day? So, Paul.
Well, no, thanks. I think it's been great. I think this discussion's been super, actually. I think we touched on a lot of things, and we could probably carry on for some time. But no, it's very good. And I'm thinking, especially after hearing you, Laurence, and the various measures of polarity, lipophilicity, and then that contribution of functional groups to the profile of the molecule, I think it is very interesting, and there's going to be more to learn about that. So that was one of my major take-home messages today. So thanks for that.
Thank you. For me, it was more kind of seeing the trend of how where people kind of the work on the molecules, and what is the trend when we say we don't want to say beyond rule of 5 anymore, but more, you know,
No.
so exactly that. I think we all agree on that. But yeah, to see the trend of higher molecular weight, but still control of lipophilicity, and it's kind of very insightful.
I would agree. The term beyond rule of 5 is unfortunate. I guess it's a tag that people allow. But, you know, we're talking about a continuum, really, aren't we? A continuum of properties.
Absolutely.
You know, and all the things we've been talking, this big interest in large molecules, you know, is beginning to be uncovered now. And probably the rule of 5 held back this investigation, actually, because people didn't believe you could go there. And that's not, we knew that before the meeting. But I think that's an important message for folks, actually, to think of things as a continuum, not as a hard cutoff.
As a hard cutoff, yeah. Agree.
Yeah.
Agree. Thank you so much. Thank you so much, everyone. And we will be happy to see you tomorrow. I'm excited about hearing to Giacomo and Rob's talks, because it will be plenty of insights again. Thank you so much, and see you tomorrow. Bye, everyone. Hope you will be
Thank you very much.
Right,
Thank you very
bye.
much.
Bye. Thanks a lot.
Bye.